Recall that chemistry is the study of matter, and matter is anything that has weight and takes up volume. Now, matter can be broken down into two general categories: pure substances, and those are materials essentially that can be represented with a single chemical formula. And then there's a category of mixtures, and that's where you have two or more pure substances added together, but each of those substances maintains their identity. So in other words, if you've mixed water with salt, the water remains water and the salt remains salt. They don't chemically react to form something new. Now, each of those categories can be further divided into classes. Pure substances, there's two types. There are elements and there are compounds. Now, the general progression is we think about elements as making compounds, and from compounds we make chemical mixtures. But back to pure substances. So elements, for example, we may have hydrogen and oxygen, and we can combine those to make the compound known as water. Or we could take elemental sodium and elemental chlorine, and we could make sodium chloride table salt. Or we could even take something like carbon and hydrogen, and we could make octane, a key component in gasoline. Notice, all of these are pure substances because each one of those things that I mentioned can be represented by a single unique chemical formula. So let's look at how we can form a homogeneous mixture or a heterogeneous mixture. Let's say we chose to mix water and sodium chloride. What are we going to get? Salt water. And one thing you will notice if you actually choose to drink or swish this in your mouth for whatever reason is that it's homogeneous. That is to say, it's one phase. If you look at it, it looks like a single phase, but you could put it to the test. Are the phases the same? Is it really one phase? If you tasted a sample from the top and you tasted a sample from the bottom, indeed, they would taste to have exactly the same amount of saltiness. That is to say, it's one phase. It's homogeneous throughout. As opposed to a heterogeneous. So let's say we mixed water and we mixed oil, octane. What you will notice in that case is that you get two phases. You will have an octane or an oil layer, and you will have a water layer. So you will easily be able to distinguish the heterogeneous mixture because it is noticeably two-phase. Notice with homogeneous, the water stayed water and the salt stayed salt. And in the second case, the oil layer, the octane, stayed octane and the water stayed water. These did not combine to make some new chemical reaction. They maintained their original identities, and hence we have a mixture. Let's practice. See if we can identify some. Pure apple juice. What is that? Well, it's a mixture. We know it tastes sweet, so it's probably got sugar in it. We know it's not clear, so it probably has some color bodies in it. So we know there's at least two things in our mixture. We're guessing probably correctly that there's a lot of water in it. So we know it's a mixture, but is it homogeneous or heterogeneous? Well, if it's the kind that you buy in the grocery store and it has one nice phase, you know that it's a homogeneous mixture. Table salt. What is that? It's a compound. Table salt is NaCl is the formula, sodium chloride. Table salt can be represented by one specific molecular formula. Well, if everything in the world falls into those 4 classes, then a chocolate chip cookie must fall into one of those classes. And you can probably guess. First of all, you know that it's a mixture. Why? If you've seen the recipe, you know there's a bunch of things that go into it. So it's a mixture. What kind of mixture? Well, it's obviously a heterogeneous mixture. You can see parts of it that's just the chip, parts of it that kind of has a different texture and look than other parts. And so clearly it doesn't look the same all the way across. And it doesn't taste the same. If you just take a little bitty bit of the chocolate chip, it's going to taste a lot different than if you just take a little bitty sample of the dough. Brass. That's a tricky one. It's actually a mixture of copper and zinc. The copper actually stays copper and the zinc stays zinc. So whereas we reacted sodium plus chlorine and it gave us a new compound, we don't have copper plus zinc giving us a new compound. That doesn't happen. The copper stays copper and the zinc stays zinc. So even though it's a solid and even though it's a metal, it is still a mixture. And because if you take a cross section of brass and you look, it looks exactly the same. And if you analyze it, it's going to analyze almost exactly the same no matter where you take a piece from. So it is a homogeneous mixture. Here's a very weird aside for you. A homogeneous mixture is given a very special name. And a homogeneous mixture is the same thing as a solution. So what that means is a piece of brass is actually a solution, despite the fact that it's a solid. So beware. Solutions can be mixtures of solids, liquids, and gases in different proportions. Gasoline. That's a mixture. And you hope it's a homogeneous mixture. A gas has literally hundreds and hundreds and possibly thousands of components if you analyze it. But it should look exactly the same. That's another reason why you do not want water in your gasoline. It actually makes 2 phases. The water sinks to the bottom, and your machine or whatever you're using the gasoline to feed could possibly pull high amounts of pure water, and that will mess up the equipment. So you need what's typically referred to as dry gasoline. Maple syrup, it's a mixture, and that's homogeneous. Olive and vinegar dressing, that's an easy one to classify generally. Of course, it's a mixture of oil and vinegar. But the oil phase floats on top of the vinegar or water phase, and so we wind up with a heterogeneous mixture. And there's the problems we just went over with the answer written in a little neater form.